Today I'm going to go over your AP Precalculus topics, starting at 1.7 through 1.11, primarily about rational functions. So the first thing we're going to look at is the end behavior of rational functions, and we're going to answer in limit notation. So let's talk briefly about what happens. At the ends, as we go to infinity and then we go to negative infinity, it depends on the degree. So there's three cases here. If the degree of the numerator is equal to the degree of the denominator, then they're growing at basically the same rate. So what takes over is the leading coefficients. Okay, and if we're writing the equation of the line, it's going to be a y equals. When it's in our limit notation, it's just going to be the value. Second case is if the degree of the numerator is smaller. That means the bottom's going to be growing a lot faster, which means it's going to end up going to 0. Versus if the degree of the numerator is bigger, then that top's going to grow faster. So the end behavior is going to match our reduced form. But there is no horizontal asymptote. All right, so let's look at these three. This has an example of each of the three cases. So the first one, we have a degree 2 over degree 2. So the leading coefficients are going to take over. So the horizontal asymptote is going to be at 3/4, but this is asking us to describe the end behavior. So end behavior, whether we're talking about a polynomial, we're talking about a rational function, whatever, we're looking at g of x. The limit as x goes to negative infinity, and the limit as x goes to infinity of whatever function we're looking at. Okay, that's always end behavior. For this particular one, for both ends, it's going to approach that horizontal asymptote of 3/4. Okay, here my degree is bigger on the bottom. So I have a horizontal asymptote at y equals 0, and that will dictate my end behavior. Okay, we're going to 0 as we go to both positive and negative infinity. This last one, the degree is bigger on the top. So it's not going to have a horizontal asymptote, but we can still determine the end behavior. What I'm going to do here, all this stuff that's not the highest power, I don't really care about it as we get really, really big or really, really negative. So this is essentially the same as x to the 7th over negative 2x to the 6th, again for big values. If I were to reduce this, we'd end up with x over a negative 2 or a negative 1/2 x. So the functions at the end behavior is going to behave the same as negative 1/2 x. Well, negative 1/2 x is just a line with a negative slope. So as we go to positive infinity, it's going to go to negative, and as my x values go to negative infinity, my function is going to go to positive. So negative infinity is going to go to positive infinity. And as we go to positive infinity, as our x goes to positive, my h of x goes to negative infinity. Next, we're going to look at the zeros of a rational function. Zeros are always values that if you plug a number in, your output is a 0. Graphically, it's going to be on the x-axis if it's a real value. For our rational functions, it's going to be whatever makes the denominator 0, with the exception of any wholes that we might be able to cancel out. So if we have a common factor in the top and the bottom, we'll have a whole, and we'll get into that in a minute. So we remove that. Anything that's left that makes the numerator 0 is a 0 of our function. So x equals 8 will make that one 0. Here, we want to figure out first if there's any wholes that we can cross off, and also what values make the numerator 0. So we're going to factor here. So we have a common factor of x I can pull out. That gives me an x squared minus 4x minus 5, which factors like so. Our denominator factors to that. So again, I have a common factor, so we're going to take that out. And here we're going to have two different values that will make the numerator 0. 0 will make x 0, and negative 1 will make that factor 0. Okay, next we're going to take those same two equations and investigate any holes that we've already talked about and any vertical asymptotes. So holes are where there is a common factor in the top and the bottom, and it completely reduces out. Had this been like a squared, then you're not actually going to have a hole there because you're still going to have an x plus 5 in the bottom. But for our purposes, we have a hole here at negative 5 and a vertical asymptote. Vertical asymptotes occur when the denominator is 0. So in this case, at x equals 3. Again, unless we, if it doesn't cancel out, then we would have more than 1. Okay, this one's the same one we just factored. Okay, so this one has a hole at that common factor, so at x equals 5. In the denominator, the only thing that's left is this x plus 3, which makes x equals negative 3 a vertical asymptote. And you can have multiple vertical asymptotes. There's a limit of 1 horizontal, but vertical, we can have as many things makes the denominator 0. That leaves us with slant asymptotes. So we're going to find a slant asymptote. That's going to occur in the third case with the end behavior of if the degree is higher on the top by exactly 1. Okay, it can be 2 over 1, 3 over 2, 20 over 19. As long as it's exactly 1 higher, our graph is going to approach a line that is not a vertical or horizontal. It is a just normal slanted line. To do this, we're going to do polynomial long division. Okay. So we're going to actually do this division. We're going to divide 2x squared plus x minus 1 by x minus 3. So just like regular long division, you're looking at what would I multiply this by to get this, which would be a 2x multiply down. Okay, I'll put that in parentheses, and we're going to subtract. This should always equal 0 if you picked the right thing. Then we have x minus a negative 6x, so that's really x plus 6x, or 7x. Then we look at what I'd multiply this by to get this, which would be 7. Now, the long division itself has more steps. We would multiply down and get a remainder and all of that. But the purpose that I'm using this long division for is to find the equation of my slant asymptote, which as soon as you have mx plus b, we're done. Again, the division is not complete, but the part of it that we need is. So let's do another. You can try to see if you want to do this, if you can get this one on your own. Okay, so to get x squared, we're going to multiply by x, multiply down, subtract. X squared minus x squared is 0, good news. 3 minus a negative 2 gives me a 5x. So I'd multiply x by 5 to get that. And we can stop there for this particular situation, because I just want the equation of the line. Now we're going to put all of those pieces together. We're going to investigate a lot of different pieces, but the primary tool here is to factor. So we will factor this. Okay. Then that gives me the information I need. So zeros are anything that's going to make the numerator 0 except if there's a hole. So we've got a common guy here and here. so just x equals 8 for our zeros. The whole is going to be at x equals -2. The verticals, we're left with x plus 4, so x equals -4 will be my vertical asymptote. Horizontal, I like to go back to the original one, but it doesn't really matter. You'll get the same thing. We have the same degree on the top and the bottom, so it's going to be the ratio of the leading coefficients, which is 1/1. So this is going to go to y equals 1. So vertical is an x equals line. Horizontal is a y equals line. There is no slant asymptote because that only occurs when there's not a horizontal in the specific case where the degree is bigger by 1, and this is not that. And then the domain. The domain is any value that isn't going to be undefined, and the things that are going to be undefined are the two values that made the denominator 0, the whole and the vertical asymptote. So I'm going to say all real numbers except x equals -2 and x equals -4. All right, on to our next one. Zeros. Let's go ahead and factor this first just to make sure we don't have some canceling. Okay, so the only way I can get a 2x squared is with a 2x and an x. The only way I can get a +1 is with a -1, well, a +1, or -1. Anyway, so we do not have any canceling. So the zeros are going to be what makes this numerator 0. So if I set 3 or 2x plus 3 equal to 0, we'd subtract 3 divided by 2. So x equals -3/2. There are no wholes in this one because there are no common factors on the top and the bottom, which means I have two vertical asymptotes. The thing that makes that 0 is 1/2, and you can set up an equation to do that if it's not in your head. X equals 1 for that guy. Horizontal, the degree is bigger on the bottom, so this one has a horizontal asymptote at 0. It does not have a slant asymptote. And the domain is, again, all numbers. All real numbers except x equals 1/2 and x equals 1. Okay, we'll do one more. Again, we're going to factor. We have a common factor here of x. And then I have x minus 7, x plus 1. And then on the bottom, x minus 4, x plus 1. So we have two zeros. We've got our whole at x equals -1. So we'll take that out of our piece. Zeros are going to be x equals 0 and x equals 7. Vertical asymptote, x equals 4. The degree is bigger on the top than the bottom, so there is no horizontal asymptote, but there is going to be a slant asymptote. Now what I'm going to do, you could do the division with this original one, but I'm actually going to do my division with my reduced form here. You'll get the same answer either way. Okay, so we'll go ahead and do the division off here to the side. We'd multiply by x to get that. So a -7 plus 4x is a -3x. So we get a slant asymptote of y equals x minus 3. And finally for the domain, everything's in except for the whole -1 and the vertical asymptote 4. And you could also state this with inequalities and do an interval. I just find it faster just to state what isn't in the domain rather than what actually is in the domain. Next, we are going to write an equation with specific information. So looking at this, we have a function that has a 0 at x equals 1, a whole at x equals -3, vertical asymptote at 5, and a horizontal asymptote at y equals 0. So let's start building this up. Okay, if we have a 0 at 1, that means in my numerator, I need an x minus 1. Okay, whole at -3. We're going to have an x plus 3 on both the top and the bottom. Let's make that happen. Vertical asymptote at x equals 5, which means in the denominator, I need an x minus 5 to make that happen. And finally, a horizontal asymptote at y equals 0. That means I need the degree of the numerator to be less than the degree of the denominator. And right now, if I were to FOIL this out, I'd have a degree 2 over degree 2. So I just need to make this denominator bigger. You can do that in a number of different ways. I'm just simply going to multiply by x, but you can multiply by whatever you want as long as you have raised the degree of that denominator. Okay, let's do another. Okay, so I have a whole at 3. Vertical asymptotes at x equals 0 and x equals -5, which means x is a factor and x plus 5 is a factor. And you can put them in different orders. It just feels awkward to put the x after. It doesn't matter though. And finally, a horizontal asymptote of y equals 2/3. So there's two things that we need to address here. First, if it has a value other than 0, that means the degree of the top and the bottom have to be the same. And right now I have a degree 1 over a degree 3. So I need to bump this up to a degree 3 to match it. Then we need to adjust the 2/3. So that means I need the ratio of the leading coefficients to be 2/3. So I will simply just put a 2 on the top, a 3 on the bottom, and we're going to be good to go there. Okay, I'll do one more here. 0 at x equals 12. So x minus 12 is a factor on the top, no whole. Vertical asymptote at x equals -4. So x plus 4 is in the bottom. And it has a slant asymptote, which means the degree of the top is exactly 1 higher than the degree of the bottom. So right now I have degree 1 over degree 1. So I want this to be 1 higher, which I can accomplish by just multiplying by x. All three of those, there's multiple correct ways to get those, or multiple correct answers, but those are some examples. All right, so here I have a graph of a rational function that features a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 2. And one thing we're going to talk about is how do we, and we've already done the limit statements for the horizontal, but what do we do for the vertical as well? So for the horizontal asymptote, that's the end behavior. We're looking at the limit as x goes to -infinity and the limit as x goes to +infinity. Okay, so as we go to -infinity, my graph is approaching that horizontal asymptote of 2. As we go to +infinity, my graph is approaching that horizontal asymptote. And that's how we can detect a horizontal asymptote. If you have a limit that goes to a value, that is the definition of a horizontal asymptote. For the vertical asymptote, we're not going to infinity, we're going to 1 in this case. So I'm going to look at the limit as x approaches 1 from the negative side. So we put a little minus guy there to indicate that. And we're going to do the same thing. We're going to go to 1 from the positive side. Okay, so as I approach 1 from the negative side, as we approach it from values a little bit less than 1, these values are increasing without bound, which we say means we're going to infinity. If we're approaching 1 from the positive side, those values are decreasing without bound, so we say that's going to -infinity. Next, we're going to be solving some rational inequalities here. So we want to figure out when this whole thing is in this case, greater than or equal to 0. And that equal to, that's an important piece we need to pay attention to. There's different ways to organize this. I like to organize this with number lines. So I'm going to write a number line for each one of my factors. So this just breaks down what happens in each one. Then I'm finally going to have one for the overall combination of all those pieces. So then I want to identify what my zeros are. So my zeros are -5, 2, 0, and 4. Now not all of those are zeros, and we'll talk about that. But those are the values that if I plug them in, each of the independent factors are going to be 0. So in this number line, I'm going to put those numbers in numerical order. Okay. For my function, the things on the top are going to give me an output of a 0. The things that make the denominator 0 are going to be undefined. So on my number line chart here, I just put a little x, because that's not going to be included in anything, because our function is undefined there. Then on my other number lines, for the corresponding value to each factor, I'm just going to place that thing, that number, in the same position I have it on my number line chart here. Okay, then I'm going to go through each factor and look at what happens. These are all linear factors, so they're all going to change from negative to positive or positive to negative. You can think about the graph or pick a test point, but all of these, there's nothing funny going in. If I plug a number in less than -5, I'm going to get a negative value. Plug in -10, you get negative. If I plug in a number bigger than -5, like 0, I'm going to get a positive value. This one will also go from negative to positive at 2, negative, positive, negative, positive. Where that'll switch is if you had like 4 minus x or something like that, or if you have a squared, then it's going to behave a little bit differently. Now we're going to look at what happens when we combine them. Okay, my function is this number times this number divided by this number times this number. So if I break that down, I'm going to have a negative times a negative on the top, which would give me a positive. On the bottom, I'm going to have a negative times a negative, which would be positive. And a positive over a positive is positive. We'll just do that for each little section. On the top here, I'm going to have a positive times a negative. So we'll have a negative over a negative times a negative, which gets me negative values there. Here I'm going to have a negative over a negative, which gives me a positive. Here I'm going to positive, positive on top, positive, negative on bottom, so we get a negative. And then everything's positive over positive is a positive. So that's what it's behaving. Then we want to select our winners. Okay, we want this to be greater than or equal to 0. So greater than is going to be the values where we got positive values. Equal is anywhere where it also equals 0, which is going to occur at -5 and 2, but not at 4 and 0, because those ones were in the denominator. So this is going to be x is less than or equal to 5, because it is 0 at -5. Here, we're going to have 0 is less than x is less than or equal to 2, because 2 is in the club, because it's as a 0. 0 is not, because it's undefined. And then 4, x is greater than 4, non-inclusive. Let's do another. Okay, this one I'll need to factor first. So that's going to be an x minus 5, x plus 4. Then I'll do my number lines. And again, there's different ways to organize this information. This is just what makes sense to me. We've got -4, 3, and 5. Okay. On this one, -4 is not included, 3 is 0, 5 is undefined. So I put that there to make sure we're good to go. These are all going to go from negative to positive. I didn't do anything clever here. Okay, and then on the top, so we have the top number divided by the product of the denominator. So we're going to have a negative over a positive, which will give me a negative. I'm going to have a negative over a negative, which will be a positive. I'm going to have a positive over a negative, which is negative, and we'll have a positive over a positive, which is positive. And we pick our solutions. We want when x is less than 0. So we're looking for the negatives in this case. We have when x is less than negative 4, and negative 4 is not going to get included no matter what. Here, the 3 is not included for this one because my inequality is simply when it's less than 0. Okay. And lastly, in section 1.11, we've got the binomial theorem in there. So let's talk binomial theorem. Binomial theorem revolves around Pascal's triangle, which is developed by adding the two numbers above. For my two problems, I need to row 5. So here's how I like to do this. The coefficients of my binomial expansion are going to come from Pascal's triangle. So I'm going to the 4th power, so I'm going to take the 4th row of Pascal's triangle. Okay. Next, I'm going to take the first thing in the binomial, and maybe I should have talked about a binomial is when you have two things in there. Binomial. Okay. I'm going to take the first thing, which is 2x, in its entirety and raise it to the power of whatever the power is. Then we're going to do that again, but we're going to decrease by 1 each time. So we'll have 2x cubed, 2x squared, 2x to the first, 2x to the 0 is going to be 1. Then we take the second thing, which in this case is a 1. There's not going to be a 1 in the first. We'll have a 1 to the 1, 1 squared, 1 cubed, 1 to the 4th. And you should always end at the power that we're working with here. So we've expanded it, but now we need to do some good old-fashioned simplification. 2x to the 4th. That 2 also gets raised to the 4th. So that's going to be 16x to the 4th. I'm going to do this in 2 steps. 4 times 2x cubed is 8x cubed times 1. 2x to the 2, or 2x squared, is going to be 4x squared times 1. Here I don't have a power I need to deal with, so I'm going to say 8x, and then 1 times 1 to the 4th is just 1. So my final step would be to do those 2 quick multiplication problems. And that's how we can use the binomial theorem to expand. Let's do one more. So I take the 5th row of Pascal's triangle this time. So 1, 5, 10, 10, 5, 1. The first thing is x, so we'll have x to the 5th, x to the 4th, x cubed, x squared, x, no x. Then we're going to take 2. There's no 2 in the first one, but we're going to have a 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and then we simplify. Okay, I'm going to have 10x cubed times 4. We'll come back and simplify that in our next round. Times 8. 16. 2 to the 5th is 32. Uh, 4 times 10 is 40. 10 times 8 is 80. 5 times 16 is 80. Plus 32. So this is AP Precalculus, topics 1.7 through 1.11. Thank you for watching.